Hi everybody, in this lesson we're still going to be focused on calculating confidence intervals, but this time rather than using population data, we're going to be working with a relatively small sample. Here are the questions for this lesson. First, what's a t-distribution and how is it different from the standard normal z-distribution that we looked at in lesson 1? And second, how do we use this t-distribution to calculate a confidence interval when we have a small sample size and when we don't know the true population parameters? Let's start with a recap from lesson 1. You'll remember that in order to calculate and use z-statistics from a standard normal distribution, we have to assume a few things. First of all, we need to know the population parameters. In particular, we need to know the population mean and the standard deviation. We also need to assume that the sample we're using is both sufficiently large and that the sampling distribution is normally shaped. In Lab 3, where I just gave you a critical value and told you to plug it into an equation, we just went with these assumptions because we had a very large sample that we were working with. But in reality, these assumptions don't hold, particularly if we have a small sample size. We're not able to just assume that our sample mean and our standard deviation, which you now know how to calculate in Excel, approximate the population parameters. We can only do this if we have a sufficiently large sample. In the one that you were working with, there were hundreds of thousands of observations. But as you'll see in this lesson, when we say sufficiently large, we're usually talking about a sample size between 500 and 1,000, much smaller than the one that you were working with. If you have less than this, though, we need to get those critical values that we plug into our confidence interval equation from somewhere else. So, to calculate a confidence interval using data from a smaller sample, again, we need a formula and a probability distribution. This time, though, we need our probability distribution to make adjustments for uncertainty based on our small sample size. And where we get these critical values is from something called a t-distribution. What I've got here on the screen is the equation for calculating a sample confidence interval. And you'll notice that it looks remarkably similar to the one that we looked at in lesson 1, or the one that you used to calculate a 95% confidence interval in lab assignment 3. The notation's just changed a little bit. Here, the Greek letters refer to sample statistics as opposed to population parameters. So again, we can interpret this equation as y bar plus or minus t times the sample standard error. That is to say, we're going to take our mean from the sample and add and subtract a t critical value times the sample standard error, which again, you know how to calculate in Excel now. So all this is to say, this is essentially the same formula as we looked at in lesson 1. We're just using sample statistics rather than population parameters, and this time we've got a t value instead of a z value as the critical value we're going to plug into this equation. So we want to ask, where does this t-statistic come from? Well, just like with the z-distribution, the t-statistics comes from a corresponding probability distribution. And unlike the standard normal distribution that we looked at in lesson 1, the shape of the t-distribution actually varies depending on the sample size that we're working with. So we'll see that in larger samples, anything above 200, the t-distribution starts to look a lot like the z-distribution. This is why we can use z-scores with really large samples. But as the sample gets smaller and smaller, the t-distribution starts getting flatter and wider and thicker in the tails. We'll look at what all of this means here in a second when we go to the table itself. So this time we need to know the sample size and the confidence level we're working with. And you'll see that once we know these things, the t-table is actually a little easier to use, at least in my opinion. All right, so how do we use this table? Well, you'll remember that in the z-table, we had to divide the remaining 5% if we were calculating a 95% confidence interval in half. And that's because the z-table only looks at probabilities in the right-hand tail. But in the t-table, once you open it up and look at it, it's in the appendix of your book, just like the z-table, you'll see that the critical value for a one-tailed test at alpha level 0.025, which would be the upper bound in the z-table, is the same critical value as a two-tailed test at alpha level 0.05. So 1 minus the confidence level that we're looking at, 1 minus 0.95, is 0.05. This is the leftover probability, the uncertainty that's remaining in both tails of the distribution. I keep using the term alpha. Alpha just refers to 1 minus the confidence level. And then other than that, the only other thing we need is something called the degrees of freedom. And degrees of freedom, the way we calculate that, varies depending on the type of statistic that we're trying to calculate. In this example, though, degrees of freedom is simply n minus 1, or the sample size minus 1. And again, you'll see what this means here in just a minute. So let's go to the table. Again, this is listed in the appendix of your textbook, but you can also easily find t-tables just by doing a quick Google search. They all look like this, more or less. Let's say that we want to construct a 95% confidence interval given the following hypothetical information. Let's say that we survey 30 people and ask them how they feel about Congress, using a similar 100-point feelings thermometer, just like you were working with in Lab Assignment 3. And from this sample of 30 people, we calculate the following sample statistics. Again, we can do this using Excel, things you've already practiced doing. We can use Excel to figure out that our sample mean is 64 in this hypothetical distribution, and our sample standard deviation is 11. So we're going to take this information and we're going to go to the t-table to find out what critical value we need to plug into our equation. And the first thing I have highlighted on this t-table is at the very bottom. You'll notice that as degrees of freedom, which remember is the sample size minus 1, as that number approaches infinity, the t-distribution looks the same as the z-distribution. We see that same 1.96 critical value associated with a 0.05 alpha two-tailed test. And even if we have a sample size that is not quite approaching infinity, even something like 120, we see that the critical value is getting really close to that critical value we got from the standard normal distribution. In this case, 1.98. So close, but not exactly that critical value. However, we don't have a sample anywhere near that large in this case. We only have 30 people that we asked this question for. So given that we want 95% confidence, which remember, because we're calculating a confidence interval which has a lower and an upper bound, we're going to be looking at a two-tailed test with an alpha level of 0.05. We find that column on the t-table. We go down until we get to the degrees of freedom of 29, which is 30 minus 1 in this case. And we see that the t-statistic we need to plug into our equation is 2.045. So let's take that information and construct our confidence interval. Again, recall the equation for calculating a sample confidence interval. We've got y bar plus or minus t times the standard error of the sample, which is just the sample standard deviation divided by the square root of n. Again, all things you can calculate in Excel to just plug into this equation. So we do all of that, and we see that our confidence interval is going to be equal to 64 plus or minus 2.045, our t-value from the table, times 11 divided by the square root of 30. We plug all that in, we get something looking like 64 plus or minus 4.107. And we can say that given our sample, we can be 95% confident that the true population mean falls somewhere between about 59.89 and 68.11. To recap the main points from this short lesson, we've said that when we have a small sample size and we don't know the true population parameters, we have to use a different distribution. In this case, we use what's called a t-distribution to find the critical values we need to plug into our confidence interval equation. We also saw that as the sample size starts approaching infinity, the t-distribution and the z-distribution look the same. This is why, in reality, if we have a sufficiently large sample size, really anything between 500 and 1,000, it's pretty safe to assume that the sample statistics we calculate approximate population parameters, and we can use a z-distribution to calculate our confidence intervals. But when we have these smaller samples, we have to go to this different table and find a different critical value statistic in order to calculate a confidence interval.